In the third part of the first lecture of week 11, I would like to show you another way how to solve non-homogeneous differential equations using Laplace transform. So here let's consider the following example of general non-homogeneous differential equation with constant coefficients a, b, and c, and the initial values are just zeros. What do we have in this case? If we apply Laplace transform to both sides of this equation, what do we obtain? We can use here linearity and also the theorem Laplace transform of derivative. So we know that, for example, Laplace transform of second derivative at a point s, this is s squared Laplace transform of the function at a point s minus s y of 0 minus y prime of 0, which are just zeros. So this is just s squared y of s. Similarly, Laplace transform of the first derivative is just s y of s. So we get a s squared y s plus b s y s plus c y s. And on the right hand side we get the Laplace transform of the function g. Let's for simplicity denote this capital G of s. So now if we take out the Laplace transform of y, we get the following quadratic expression. And so Laplace transform of y is 1 over a squared plus bs plus c times the Laplace transform of gs. And this function here usually is denoted as h of s. So y of s is h of s times g of s, where h of s is a function like this, and its name, it has a special name, it's called transfer function. The function can be easily constructed just looking at the equation. So as you remember, we constructed characteristic equation. So this is 1 over characteristic equation here. So you see the coefficients here are the same as the coefficients of the equation. And since after that, to solve the equation, we have to find inverse Laplace transform of this function. So for simplicity, the small h of t, this is inverse Laplace transform of h of t, and it also has a special name. It's called impulse response function. Impulse response function. And if we now write the solution y of t, this is the inverse Laplace transform of h times g at a point s, and using the inverse Laplace transform convolution theorem, we know that this is convolution this is h convolution with the function j at a point t. So the solution of this particular initial value problem is h convolution g at a point t. So this we are going to use later. Okay, so to find solution of this problem, we need to find impulse response function and take a convolution with the function j, which is on the right hand side, and that's it. Let's now consider more general case. So for general, we have just homogeneous equation with some arbitrary initial values, so some general initial value problem. What can we do for this case? We combine, to solve this, we combine two initial value problems. The first one, the initial value problem with zero initial values, which we just considered. And when we solve it, let's say we got y1, which is, as we remember, this is the convolution of the impulse response function and the function j. Together with the first initial value problem, together with the initial value problem for homogeneous equation, so 0 on the right hand side, but the initial values are the initial values which are given originally. And of course we can solve this homogeneous equation. We know how to solve it, and we obtain some homogeneous solution. And then the solution of sorry, I think it is better to use 1 here. Maybe we will use, say, something here and maybe h here. So the solution with the wave, the solution of this initial value problem, which contains the same equation but the initial values are zeros, and the solution of homogeneous equation with the original initial values. And then the general solution, the solution of original initial value problem will be the sum of these two. We can check this easily if we substitute y into first. Into the original initial value problem, we get that y satisfy the equation plus b y prime plus c y plus yh, which gives us a y double prime plus b y prime plus cy with wave plus a yh plus b yh plus c yh. And this part here, because y with wave is the solution of non-homogeneous, equals to g of t, and this part here, because yh is the solution of homogeneous, gives us 0, so we obtain g of t. So indeed y satisfy the equation. And let's look at the initial values. Y of 0 is y with wave at 0 plus yh at 0, and y with wave at 0 is 0 because y with wave satisfy this initial value, so this is 0, plus yh satisfy this initial value, so this is y0, and similarly y prime of 0 is y1. So indeed y satisfy the initial value problem that we considered at the beginning. So in summary, what should we do to solve such initial value problem? We solve two initial value problems. The first one can be solved finding the impulse response function, and the second one, this is just standard homogeneous equation which we know how to solve. Let's consider an example. Yes, and at the end, of course, we combine them as a sum. Okay, so let's move to the example. So to solve this initial value problem, first we will solve the initial value problem, the same equation, but the initial values are zeros. So and how we solve this, we find the solution as the convolution of the impulse response function together with the function g. And let's find the impulse response function. This is inverse Laplace transform of the transfer function, which is 1 over, and here we write the same coefficients, the quadratic expression with the same coefficients, yes, that we have in the equation. So this is s squared plus 2s plus 5 at the point t. And to find this inverse Laplace transform, let's rewrite this expression inside to make it looks like expression in a table. So we complete square here, and what's left here, 5, so 1 comes into the square, and left is 4, so this is 2 squared. And to get sign, we need to multiply by 2 here and divide by 2, so we obtain this expression. And now we have exactly this formula in the table: 1 over 2 e to the minus 1t, so minus t, times sine of b, which is 2t. And so the solution is the convolution of h and g. So this is a half e to the minus t minus v sine 2t minus v and g of v dv. So the solution of the first initial value problem is here. So this is y with wave. And second, what we do, we solve the initial value problem with homogeneous equation, and the initial values are the same as we had originally. And to solve this, we need to write, of course, the characteristic equation first. And the solution of this equation are two roots. We have two roots. So minus 2 plus minus square root of the discriminant is 4 minus 20, which is minus 16. Everything is over 2. So we get minus 1 plus minus square root of minus 16 is 4i, right? 4i. So with 2, this is 2i. And so the solution of homogeneous is c1 e to the minus t, say cosine 2t, plus c2 e to the minus t sine 2t. And to satisfy the initial values, we have to find the derivative, of course. Okay, this is, let's take this out, minus t out of the brackets, we get minus c1 cosine 2t minus c2 sine 2t. Then the derivative of cosine is minus sine, and with this coefficient 2, so minus 2 c1 sine 2t. Derivative of sine is cosine with the coefficient 2, so plus 2 c2 cosine 2t. Okay, so let's now satisfy the initial values. Y of 0 is 2. So 2 is, instead of t, we put 0. This part with sine is 0, with cosine is 1. So 2 is c1. And for derivative, we have minus 2 is, we substitute 0 into the derivative. This e to the 0 is 1. And what do we have here? We have non-zero where we have cosine. So we have minus c1 plus 2c2. So as we know that c1 is 2, so we put 2 here, we get that c2 is 0. So the solution of homogeneous initial value problem is c1 is 2 e to the minus t cosine 2t. So the solution of the original one, y of t, This is the sum of the first y with wave. So this is a half integral from 0 to t e to the minus t minus v sine 2t minus v g of v dv plus the solution of homogeneous. Okay, so this is the solution of the given initial value problem.